130. This is our 5th lesson in the acids and bases unit. This is Ka and Kb versus pH and pOH. Today we're going to look at a few reminders about pH from Chemistry 20. Then we'll move forward to the relationship between pH and pOH. And we will have 6 examples throughout the lesson today. The potential of hydrogen. pH is a logarithmic scale from 0 to 14. More acidic solutions have lower pH values, while more basic solutions have higher pH values. The two equations that involve pH are pH equals the negative log of the concentration of H3O+, and the concentration of H3O+ is equal to 10 to the exponent negative pH. When working with weak acids in equilibrium systems, the concentration of H3O+ in both equations will be the equilibrium concentration. For logarithmic values such as pH, any digit to the left of the decimal is not significant. So a pH of 1.23 has 2 significant digits. Only the 2 and the 3 that are right of the decimal count as significant. A pH of 7 has no significant digits because there are no numbers to the right of the decimal. Now let's take a look at the relationship between pH and pOH. First up, we have our two equations that involve pOH. Again, they are very similar to pH. pOH equals the negative log of the concentration of OH minus, while the concentration of OH minus is equal to 10 to the exponent negative pOH. When we work with weak bases at equilibrium, the concentrations of OH minus in both equations represent the equilibrium concentrations. Below, we can see a scale that represents the relationship between pOH and pH. That relationship is pH plus pOH always equals 14. An example would be an acid with a pH which is equal to 1 also has a pOH equal to 13. Or a base with a pH of 12 has a pOH of 2. Example number 1. Find the pH of a solution where the concentration of H3O+ is 4.7 times 10 to the negative 11th moles per liter. Well, we know pH is equal to the negative log of the concentration of H3O, which is provided in the question. So if we take the negative log of 4.7 times 10 to the negative 11th, we are resulting in a pH value of 10.33. 2 significant digits for our answer, which is the decimal 33. And that is coming from the 2 significant digits that we are starting with in the question. The next part, calculate the concentration of H3O+ if the pH of a solution is 5.25. Well, the concentration of H3O+ is equal to 10 to the exponent negative pH, which is then equal to 10 to the negative 5.25, which is provided in the question. The concentration of H3O plus is then equal to 5.6 times 10 to the negative 6th moles per liter. Two significant digits in our answer because our question is starting with two significant digits, the 2 and the 5 that are to the right of the decimal. Example number 2. Find the pH of a solution where the concentration of OH minus is equal to 2.4 times 10 to the negative 3rd moles per liter. pOH is equal to the negative log of the concentration of OH minus. So we can find the pOH by taking the negative log of 2.4 times 10 to the negative 3rd. pOH is equal to 2.619 ... Do not round your answer yet. Then to find pH, it is equal to 14 minus pOH, which would be equal to 14 minus 2.619 ... which gives us a value for pH of 11.38. Two significant digits in our answer, the 3 and the 8, which are right to the right of the decimal because we're starting with two significant digits. The second part. What is the concentration of OH minus in a solution of ammonia with a pH of 8.10? Well, in order to find the concentration of OH minus, we must first know the pOH. So that is equal to 14 minus pH, which is equal to 14 minus 8.10. pOH is 5.90. The concentration of OH minus is equal to 10 to the exponent negative pOH, which is equal to 10 minus 5.90. The concentration of OH minus is 1.3 times 10 to the negative 6th moles per liter. Two significant digits in our answer because in the question we are starting with two significant digits, the 1 and the 0, which are to the right of the decimal. Example number 3. A 0.120 moles per liter solution of an unknown weak acid has a pH of 1.48. Calculate the Ka value and determine the unknown acid. Pause this video and attempt this question. Okay, we are back. First up, we have to determine the concentration of H3O plus from our pH value. Remember, the concentration of H3O plus for a weak acid is the equilibrium concentration. So we can sub that value into H3O plus in our ice table at equilibrium, complete our ice table, and eventually solve for Ka. So let's start at the top. First up, we need to find the concentration of H3O plus, which is equal to 10 to the negative pH. The pH was provided in the question. Our concentration of H3O plus is equal to 0.0331 ... moles per liter. In our ice table, we are starting with the initial concentration of the acid. And remember, this is a weak acid, so it reacts with water to produce H3O plus and its anion. So initially we have 0.120 moles per liter of the acid, and our products are always 0. We now have the concentration of H3O plus at equilibrium, which we can sub into our ice table. We know the initial and equilibrium values for H3O plus, so we can now find the change. And since the molar ratio for this equation is 1 to 1 to 1 to 1, the change will be the same for all species. It's going to be a positive change on the product side because we're starting with 0. And that makes our reactant side the negative change. Well, we can complete our ice table now and fill in our equilibrium concentrations. Below we can see our Ka expression, which is equal to the concentration of the products divided by the concentration of the reactants. Remember, H2O is not included because it's the only liquid in the chemical equation, therefore we do not count it. So Ka is equal to the following calculation, which then finally is equal to 1.3 times 10 to the negative second. If we look in our data booklet and compare this value to known Ka values of weak acids, we will find out that this acid is probably sulfurous acid. Example number 4. The Kb of a 0.10 moles per liter solution of aniline is 4.2 times 10 to the negative 10th. Determine the pH of the solution. Pause the video and attempt this example. Aniline is a weak base. It does not have a hydrogen that it can ionize. And we know that it is going to be a base because the question provides us with a Kb value. First up, we have to make an ice table using X for our change in concentration. Since aniline is a weak base, X will be equal to the concentration of OH minus at equilibrium. Once we know the concentration of OH minus at equilibrium, we can find the pOH. And from the pOH, we can then calculate the pH. First up, we have to start with an equation for aniline, our weak base, reacting with water, forming OH minus and its conjugate acid. Initially, we are provided with the concentration of the base, which is 0.10 moles per liter. Our products were not provided in the question, so therefore we have to assume that they are equal to 0. We were not given an equilibrium concentration for any species in the chemical equation. Therefore, we cannot find a change in concentration. So we have to assume that change is an unknown variable. Change will be equal to X. Since our products were 0, they have to gain, and they will be the positive X, making our reactants the negative X. At equilibrium, our concentrations are equal to the following. Our Kb expression is the products divided by the reactants, which is equal to X times X, or X squared, divided by 0.10 minus X. We have to check to see if the rule of 1,000 will apply for this question. The rule of 1,000 is the initial concentration of the base, 0.10 moles per liter, divided by the Kb. The Kb was provided in the question, which is 4.2 times 10 to the negative 10th. We can see that there's a smiley face, so therefore that calculation was greater than 1,000, meaning the rule of 1,000 applies, and I can get rid of the minus x from the denominator in my Kb expression. Now if we move forward and solve for x, it is equal to 6.481 times 10 to the negative sixth, which is equal to the concentration of OH minus. Once we have the concentration of OH minus, we can solve for pOH. So that is going to be negative log of 6.48 times 10 to the negative sixth moles per liter. pOH is equal to 5.188 . Now that we know the pOH, we can solve for pH. pH is equal to 14 minus 5.188 giving us a pH value of 8.81. We started with two significant digits in our question, which came from the concentration 0.10. Therefore, our answer will have two significant digits. The 8 and the 1 right of the decimal are the two significant digits. Example number 5. The pH of a 0.100 moles per liter solution of sodium carbonate is measured to be 11.66. What is the Kb? Pause the video and attempt this example. Since we are working with a weak base and we know the pH, we can first solve for the pOH. Once we have the pOH, we can solve for the concentration of OH minus at equilibrium. We can then put that into our ice table, solve for the change and the equilibrium concentrations of all species, and then finally calculate Kb. First up, to find the pOH, we are going to take 14 minus the pH. So 14 minus 11.66 gives us a pOH of 2.34. Now to find the concentration of OH minus at equilibrium, it's 10 to the negative pOH, which is equal to 10 to the negative 2.34. The concentration of OH minus at equilibrium is 4.57 times 10 to the negative third moles per liter. So we are starting with sodium carbonate, which is an ionic compound, and they dissociate in water. So that leaves us with Na plus and CO32 minus. CO32 minus is a weak base which can be found in the data booklet. So when we have a weak base in water, it reacts with water, forming OH minus. We are given the initial concentration of the weak base in the question, which is equal to 0.100. And we have to assume that our products are initially 0. We already calculated the concentration of OH minus at equilibrium, which we can then put into our ice table. Since we know the initial and equilibrium values for OH minus, we can solve for the change. Once we know the change of OH minus, we can solve for the change of all other species using stoichiometry. And thankfully, it's a 1-to-1 ratio, so the change is the same value. Since the products started with 0, they have to gain. They are the positive change, making our reactants the negative change. Then we can simply complete our ice table and solve for the concentrations at equilibrium for all species. Now we have to put our concentrations at equilibrium into our Kb expression, which is equal to the concentration of the products divided by the concentration of the reactant. So we can see our Kb calculation here at the bottom. When we complete that calculation, our Kb value is equal to 2.2 times 10 to the negative fourth. That would be 2 significant digits because we are starting with 2 significant digits from the pH value. The 0.66 are the values that are right of the decimal. They are the significant digits going into the calculation, resulting in 2 significant digits in our answer. Example number 6. Determine the pH for a 0.500 moles per liter solution of hydrocyanic acid. Pause the video and attempt this example. First up, this is a weak acid, so we are going to have to make an ice table using X for our change. Once we solve for X, it will be equal to the concentration of H3O plus at equilibrium. Once we know the concentration of H3O plus, we can then determine the pH of the solution. At the top, we are going to start with our weak acid equation. So we have hydrocyanic acid reacting with water, forming H3O plus and its conjugate base, Cn-. We are provided with the initial concentration of the acid from the question, which is 0.500 moles per liter. Our products we have to assume are 0. We do not know an equilibrium concentration, therefore we cannot find a change. Change will be an unknown variable. We will assume that change is equal to X. Since our products are 0, they have to gain. Therefore, they are positive X, and that makes our reactant negative X. So at equilibrium, our concentrations of each species are equal to the following. We can find the Ka of hydrocyanic acid in the Chemistry 30 data booklet. It is equal to 6.2 times 10 to the negative 10th. When we write out our Ka expression, it is the concentration of the products divided by the concentration of the reactants. So Ka, 6.2 times 10 to the negative 10th is equal to X times X, or X squared, divided by 0.500 minus X. So we need to check to see if the rule of 1,000 applies, and that is the initial concentration of the acid divided by the Ka of the acid. And we can see a smiley face, so that calculation is greater than 1,000, meaning the rule of 1,000 applies. We can get rid of the minus X from the denominator. When we complete our calculation and solve for X, X is equal to 1.7606 ... times 10 to the negative fifth. X is equal to the concentration of H3O plus. We then simply have to take the negative log of the concentration of H3O plus to find our pH value. pH is equal to the negative log of 1.76 ... times 10 to the negative fifth moles per liter. pH is equal to 4.75. 2 significant digits, because the lowest significant digits going into the calculation came from the Ka value, which was 6.2 times 10 to the negative 10th. That is all for today. Moving forward, we will look at titration calculations.